let me remind you a little bit about Big O. Several of your homework questions in homework number 7 ask you to show that something is Big O of something else. Show or prove. So what is it that I need to do if someone asks me that question? So I need to prove that f of x is less or equal to c times g of x for x greater or equal to k, right? So I need to actually just do anything that shows I have to find c and k for one thing. That's the first thing I need to do. And I need to just prove that inequality. I can either do it arithmetically or by induction. So if I wanted to show that x plus 5 is Big O of x, then I just need to write x plus 5 is less or equal to x plus 5x, right? And if that's true, if x is greater or equal to 1, this is equal to 6x. So therefore, x plus 5 is in Big O of x. And if you want to write your constants, c equals 6 and k equals 1, right? So those are the things that you need to do. That's a good enough proof. It doesn't have to be statements and reasons. As long as someone can read it and verify that that's true, then that's a sufficient proof. Are there questions about that?
On one of the homework questions, we had to do a summation. So would we be sort of using induction for that? That's what I tried to do.
You can use induction for that. So what was the summation on the homework? Do you remember?
Yeah, it was n to the power of k. The summation.
Oh, we had 1 to the k plus 2 to the k plus ... plus n to the k.
Mm-hmm.
Well, that's still less or equal to n to the k, replacing each of the terms, right?
Mm-hmm.
And just to indicate how many terms you have. Right? Then you do what next?
Why don't you do n to the k plus 2n to the k?
Because n to the k is bigger than 2 to the k. 2 is not a constant outside of that function. The function, the second term. So the question was, why don't I do like n to the k plus 2n to the k plus 3n to the k plus 4n to the k? Because that doesn't solve the problem as easily as this does. And also, 2 to the k is a function I can replace with n to the k without worrying about the constants. Even if n is 1, it still works. That's why I leave the constants out front. So these are not really constants in these functions. They're part of the function. That's why. So what would be the next step here? That's equal to what? That sum of n to the k's. It's n times n to the k, right? So I'm not going to finish it because then I'll have your whole homework problem sitting right up here, right? So there's only like one more step. And this only works if n is greater or equal to 1, right? It doesn't work if n's not at least 1. Right, so the last thing I wanted to mention, if there aren't any questions, I just wanted to mention if you have a division and you want to do the Big O of a function that's being divided by another function. So I want to find the Big O of f of x over h of x. Let me just be really clear. Let's just use another piece of paper. Okay, if you want to prove this, if you just want to find the Big O, just use the methods that we've already used. Like if there are any sums, replace them with each term in the sum with the largest term. So I'm going to say that the Big O of this is equal to Big O of f of x over the Big O of h of x. But that's only if you're doing very close matches for the Big O's, like if you're really doing big theta. what we normally do in this class when we're finding big O is we're really finding big theta. Whenever we replace the sum with all the terms in the sum with the largest, we're really going to find big theta, right? Does everybody feel pretty good about that? That's good. So that's what we're really doing. So this is what's really true, because not just any old functions are going to work dividing them like this. Why is that a problem? Why is division a problem with big O?
Because you're kind of reducing the size of the function.
Right. If I'm proving a less than or equal to, I can't replace the bottom with something larger, right? So if I have that, I have 1/3, or let's just do 1 over x plus 3. I can't just replace that with 1 over x plus 4 and think it's going to be bigger. Right? This is actually smaller. So it doesn't go the direction I want it to. So actually on the bottom, you really do want to make sure you're doing big theta. And if you're doing a proof, you can do it the same way. So you find the big O of the top and the bottom, but drop the constants altogether for the bottom. So that'll solve the problem, usually. Because if you have a constant in the bottom of 5 and you just drop the constant, usually you're going to have a smaller function than you started out to begin with. Let me do an example for you. Okay, so if I were just doing the big O of this function, x squared plus 5 over x plus 7, I would normally say that's less than or equal to, but doing the top, I would say that's less than or equal to x squared plus 5x squared. And the bottom, I would say x plus 7x, right? But instead of doing that, I could actually just take off this one. I can just pick the largest term and not replace the other terms in the sum, and that works. Or you can do the big O like normal and just drop the constant, because it's the same thing. But then this still is true because I've replaced the bottom with actually something smaller, which makes the total thing bigger. It's a little confusing. Whenever something goes in the denominator, it can confuse you really easily. But you just want to make sure that actually in the bottom you really want to put something smaller but close to what the bottom function is. So in this proof, I would say, that's less than or equal to 6x squared over x, which is equal to 6x. So I would say the big O of this function is x, and the constant would be 6. So I wouldn't have divided it by 8, which is what I would have had if I left the 7x in there. And this was for x greater or equal to 1, right? Okay, so that's a proof for the big O there. My constant is 6, not 6 divided by 8. So that's the only tricky part with division when you're doing big O. You can divide big O's, but make sure that you're really finding big thetas and you drop the constant for the bottom. Okay, so it's not complicated. It's just I've had some students who were asking me, you can't replace the bottom with something larger, and that's true. But since you're using big O and you're actually dropping the constants, if you just drop the constant early, you're replacing the bottom with something smaller, which makes the fraction bigger. If there are any other questions about big O, I'm ready for them now.